Okay, welcome along to Blurting video materials. Just get a few really easy bits out of the way to start with. We've got density is equal to mass divided by volume. Mass in kilograms, volume in meters cubed, density in kilograms per meter cubed. Introduces us to the idea that it's a bulk property of a solid, so all copper has the same density. It can be made into different size objects, which have masses and different volumes, but they all come back to the same density. Most of what we're concerned with in materials is what happens when we stretch a material. So we're going to imagine changing the load on a spring and plotting a graph of the force applied against the extension. So we get a straight line section, and we call that Hooke's law. So Hooke's law is that the force applied is proportional to the extension up to the limit of proportionality. And then we get the line starts to increasingly bend over. So we get a limit of proportionality, and then we get the onset of plastic deformation. If at some point we start removing the load, then the line will come back. It should come back parallel. So it's got the same stiffness. So the stiffness of the spring is the force is the spring constant delta L. So that can be called the spring constant or the stiffness in newtons per meter. And it's the gradient of that line, and because it's still got the same stiffness on the way back. However, because it's plastically deformed here, it's not going back to its original length. This is our permanent extension there. And then we can start thinking about this in terms of energy. So the energy under the line, a force times the distance, gives an energy. And then this energy here, that was the energy we could get back out. So that was the energy stored. And then this area here represents energy that was lost in the process. So this is lost energy. And then the whole area is equal to the work done stretching the material. Okay, so that's the whole process. And then from there, we're going to come back to this graph and look how it would be different if we were talking about stress and strain, but that's kind of getting ahead of ourselves. This is an object. Then the next thing we did was to think about finding the equivalent properties for the material, not on an individual object. So if you remember, we clamped a wire down, long thin wire, it has to be long to get enough extension, pulley on the end, a way of adjusting the load, maybe a mat underneath to keep the floor safe, then some kind of pointer, and then a ruler, and then we'd want to know the original length of the wire, which is from the flag to where it's clamped. The extra bit it extends is delta L, and then the force applied is mg. And then we'd either need to use a micrometer or a vernier, I think in this case a micrometer, to measure the diameter of the wire in 3 places. So we can take an average of the diameter in case the wire is not uniform either along its length or why it's circular. And then the area of the wire would be pi r squared, remembering that we found diameter, so we've got to halve it, and r would need to be in meters. So we just keep increasing the load, and we get a similar shaped graph to what we got here, but we interpret the data differently. So we're trying to work on a wire of any dimensions. So we need to introduce two new quantities: stress, which is force over area, and strain, which is extension over original length. And then the spring constant idea is replaced by Young's modulus. Measure how elastic a material is. It only applies to the elastic deformation, which is stress divided by strain. And then we can get that from this graph. I'm just going to cheekily modify this graph. Going to make that into force over area. So this becomes strain, and this becomes stress, and then that becomes the gradient of the straight line section of the graph. We need to just be able to write this, so it's F over A, just in terms of these letters can be really useful. So dividing by a fraction is the same as multiplying by the reciprocal. So we've got F over A times L over delta L. And then if we go back to look here, we're now looking at the area being F over A times L, delta L over L. So the top bit is energy, because we get a force times the distance, and the bottom bit, length times crossing, is a volume. So all these areas now become energy per meter cubed, or I think it's sometimes called elastic strain energy. So this becomes the energy stored per unit volume. This is the energy, lost energy per unit volume. And this is the work done stretching per unit volume. And it wouldn't matter what dimensions the wire you stretched were, this graph in every respect would look the same whether you used a copper wire 50 meters long, 0.1 meters diameter, or 10 centimeters long and 10 centimeters diameter. You'd get exactly the same graph. It would be very hard to do with the short wide wire, but it would still be a valid experiment. We'll sometimes see questions like this. They'll say, here's a wire, length L, diameter D, and then they'll give you another wire, length, I don't know, 3L, which is, it's not too easy, 2D, and say, if this extends an amount delta L with a force F, how far relatively does this one extend with the force F? And so the first thing we can see is, because it's 3 times as long, each with the same force, that would give us an extension 3 times more. So if the only change was the wire was 3 times more, we'd get 3 times more extension. But it's also got twice the diameter. The area of a wire is pi r squared or pi d squared over 4. Either way, it's the squared relationship. So if we go from 2d to 2d, 2d all squared is 4d squared. So it's got 4 times the area. So that was a change on its own. That's reduced the stress by factor 4, so the extension by factor 4. So the extension of this wire relative to that one is 3/4 of delta L. Right, I hope you found that useful. Thank you very much.